Okay, so we've gone over all of this in class. We talked a little bit about, the derivative and how it represents the instantaneous rate of change, also known as the slope of the line at a particular point. And that slope is important. It represents the slope of what we call the tangent line. And that tangent line, it just touches a curve just briefly at one spot. And it can tell us, what the direction that something is moving at that spot, right? So, what direction are you moving? How fast are you moving? Are you changing how you're moving at that point? And so these things we'll see them be represented as position, speed, and acceleration. And so a speed also being velocity. So right now we're just trying to get a handle on how to do one, right? And these equations look really terrifying, the very first time you see them. But like this one, we've really started to get a handle on it. We know what to do when we have an H. What we're trying to learn now, this time, is what to do. Check it out right here. He is asking us a question, and he specifically is asking, can we please use this definition right here? This is the definition he wants us to use in order to be able to do the next problem. So I'm erasing some other stuff because I just want to focus in on that definition. And remember, delta x is the same thing as an h. So if we are trying to find our limit, then we're going to plug in what happens when x is added to delta x, and then we're going to just check to see what happens just in that function in general. And we're going to put everything ready over that delta x, just like we remember putting everything over h before in class. So here we go. I'm going to make a little table, and remember I did this. I say I have an input value and I have an output value. And it's weird because right now I'm going to say I'm not even trying to plug in a specific number. I just want to plug in the function itself. So my input variable is x and my output variable will be f of x, meaning what I can plug in is x squared plus 2. That will give me my output value. Now, what if I said that I wanted to change x by a small amount? So I'm going to add a delta x. And I'll say, well, then I'm going to square something, but what I'm going to square is going to be this new value, x plus that small change, delta x. And then once I'm done squaring it, go ahead and add 2 to it. So remember, this is like a y sub 2 minus a y sub 1. And in the denominator, it's still an x sub 2 minus an x sub 1. But we abbreviate that to just be delta x. So today, I'm actually going to show you, again, how come you always get a delta x in the denominator. Because I do actually want to write down if this is my first value and this is my second value. In the denominator, I have x plus delta x, and all of that is going to be subtracting, ready, an x. And so right away, you can see that this x and that x cancel out. And so in the denominator, I'm going to end up with just a delta x. So I just wanted to prove that to you one more time. Make sure that you got a handle on that. Then what happens on top? Well, on top, I'm going to have an x squared plus, well, I'm going to have to expand, sorry. I'm going to have to expand this guy right here. Okay, and then I'm going to add 2 to it. And when I do my expansions, I use the box method. I'm going to do it like this. I'm going to say I have x plus delta x, and I have x plus delta x. And if I multiply the x's together, I'm going to get an x squared. If I multiply an x times a delta x, what I have is an x times a delta x. And what I have down here is an x times a delta x. And down in the bottom, I have a delta x being squared. Okay? And sometimes you might even write that like this with parentheses around it. I kind of like it with the parentheses around it. Like, don't forget it's delta, the change in x. These things go together. All right, so then that means that these are my like terms and they can be combined. And so on top, I have an x squared, and then I have 2 of these x times delta x terms. And again, that's all one term. So if you want to, you could actually write it without the multiplication symbol in there, or you could write it with parentheses around it. But I just want you to remember this is all one term. And then I have, ready, a plus a delta x being squared. Well, what about the rest of it? Because I forgot the plus 2. Okay, so I have a plus 2. And then what? Remember, all of that is my my y sub 2 value, right? My second y value. So this plus 2 minus is going to be minus with an x squared and a plus 2. And so now, then, what do I have? Ready? I have the limit as delta x approaches 0, because, there's that trick where I'm going to make something be equal to 0 in a minute. And I'm just trying to figure out, is there stuff that I can simplify in this top? I'm hoping that you recognize the pattern. Indeed, there is stuff on the top. What I should be able to subtract is an x squared, and what I should be able to subtract is a 2, which means that this cancels out with that, and that this cancels out with that. And all I have left on top is these two x's times delta x. I'm going to leave out the multiplication symbol because it bores me. And then here I have delta x. I will still put that in parentheses though, because I like to think of that as one unit. And then all of this is over a delta x. Now I can definitely factor out a delta x. I can factor out a delta x on the top and on the bottom. So I'm going to say that this is really the limit of delta x approaching 0. And here I'm going to say I have a delta x, and I've pulled it out in front. And what's left is a 2x and another delta x inside. And then in the denominator, remember I had that delta x, which I was looking for. My goal was to factor it out so that I can get rid of it. Just like we always have factored an h before, we're going to factor out a delta x now. And so that means that I have this lovely limit that is left, which is actually quite easy to solve. Delta x as we approach 0, ready, is 2x plus delta x, which is really just 2x plus 0, which is just 2x. Ta-da! Now, I've written a bunch of equal signs here, but I do want to mention the notation is extremely important. And on the next test, you are going to have to write the notation down, or else you are going to lose points, okay? So here we go. F prime of x, meaning the derivative of my function f. And so that's how you do it. That's the general way to find a derivative, not at a specific point. And so that feels a little bit weird right now, but as we keep moving through this, hopefully it'll start to feel a little bit more familiar. And I'll mention that you could do all of this work, but instead of using x squared plus 2, you could have plugged in that -3 and done the work and gotten an answer, which is the slope at -3. Okay, but here I just want to show you that if you have a derivative and you know what that derivative is 2 times x, and you tell me, well, I want to plug in, here, let me change this to the pink. I want to turn that into a -3, that x. Well, here you go. Then I'm going to turn that x into a -3. And my answer, when I'm all done, ready, will be -6. And it's just that easy. All right. So now the next one, he does not specify which formula you want to use. And I don't know about you, but the delta x's make me tired. So I want to do it with h's, okay? And this one, you haven't seen anything like this before, okay? So it's, well, you have. I'll mention, it's the complex conjugate. What do you mean? Well, I have a square root symbol here. So let me mention to you again that when I set up my input and my output table, I'm thinking about, ready, x is my input and delta x, and the square root of x is my output. And then I want to have a change to my x, and I didn't mean to use delta x just a moment ago. I'm thinking I want to use h's. So then I would say that inside of the square root now, I have an x plus an h. And when I'm trying to set up my difference quotient, I mentioned that earlier, that they call that a difference quotient. I want to have it be with, ready, I want to say that y prime, the derivative of y, is going to be the limit as h approaches 0 of these two things. Remember, this is my second y value, this is my first y value, this is my first x value, this is my second x value. So on bottom, I remember I always just get h, and I think that's obvious to see. All right, we've done that enough times that we know it. But on top, what do I get? Ready? I get the square root of x plus h and a minus a square root of x. Aha, the difference quotient. You're looking for some h's to cancel out. The only way that you're going to do that is by multiplying by the complex conjugate. And so right now, I'll tell you the complex conjugate is going to be the square root of x plus h plus the square root of x. And I'm doing this on top and I'm doing this on bottom. So this was tough. This is hard to remember. But that difference quotient, it's not like I'm trying to do it in the multiplying in the denominator. Remember, on top, I'm just trying to get these two things to simplify out an h that I could then, cancel. So I have the square root of x plus h and the square root of x plus h. I have the x, I have the x, and those are in square roots. So in the center here, this first term, it's just going to be x plus h. Because remember, a square root times a square root with the same radicand, that just turns into the radicand, the thing that's in the center. Down here, I'm just going to get an x. Woohoo! Yay! Okay, and oops, sorry, one of these has a plus sign and one of these has a minus sign. So there you go. There's the one that has a minus sign. And so here I had the positive version of what? X times x plus h. And here I'm going to have the minus version. And I remember those things cancel out because they're differences of squares. And so what do I end up with? Well, first of all, that x is negative. What I'm going to end up with, ready, on top is going to be x plus h minus x. Ta-da! And on bottom, what am I going to end up with? I'm going to end up with h times the square root of x plus h um, plus the square root of x. And you're like, well, that didn't really help me none. I agree. For a moment, it doesn't look like it did as h approaches 0. You know how lazy I am with my notation. Please don't do that until don't do that at the end. In between, if you lose a limit a little bit, it's not going to hurt anybody's feelings. But at the end, we want to state our limit clearly and exactly. Okay. So what I say then is, ta-da, these x's right here are going to go away. And I'm just going to have an h on top. Not only that, but it cancels out with the h that's on bottom. There is still a number on top, and that number, ready, is 1. And you're like, well, I'm not sure that that helped me any. I understand your concern. Let me write it just a little bit neater. Ready? The limit as h approaches 0 of, ready, 1 over the square root of x plus h plus the square root of x. Look, if I plug in a 0 into that h, I don't think I'm in any trouble. I don't have any division by 0. I get a thing. It's a real thing. Ready? It is 1 over x plus 0, take the square root of that, plus x, take the square root of that. Well, if you take this square root of x plus 0, you just get x. So this is really going to be 1 over the square root of x plus the square root of x, which is this. Ready? 1 over 2 times the square root of x. Now, if you start out with a nasty little function like the square root of x, I'm hoping that you understand that your derivative might look just as nasty. And also, by the way, right here, I'm going to say y prime equals. And just because I'm feeling nervous about remembering my notation, I'm going to put it over there too. Don't forget to write down that y prime, that you are telling me what y prime is, and needs to be clear in your answer, okay? So yes, the square root of x is an ugly little function, and when you take the derivative of it, it just gets uglier. But I will promise you that there is going to be a trick, and you will be able to figure these out in your head, literally in the moment, blink of an eye, okay? But I do recommend that you memorize this one. So you're going to see it on the next memorizing quiz. All right, so now that we've practiced that one, there's another one, and here we go. Given that f of t is 2 over t, find the derivative of y with respect to t. And here again, he doesn't say which one I have to use. So I myself, I plan to use that h, and I'm going to have my input, and I'm going to have my output, and I'm going to say that I have t is going in and that 2 over t is going out. And I want to do t plus h here, and I want to do t2 over t plus h there. And so now I know what my two things are, and I'm going to have something minus something on top, and it's going to be all over h, and it's going to be the limit as h approaches 0 of that. So remember, this is my second value, and this is my first value, so I'm going to put my second value in. This is 2 over t plus h, and this is going to be 2 over t. And again, I want to use a trick, and I'm not sure that you really learned it or remembered it, except for that I've gone over it in the freestyle. So if you do know this already and you didn't watch the freestyle, that's fine. But if you're watching me now and you haven't seen the freestyle, then you want to see me go over why and how I'm multiplying by what I'm multiplying by. Okay, so I want to get my common denominator, and that means right here, I'm going to say that I'm multiplying everything by t over t. And right here, I'm multiplying this term by t plus h over t plus h. And so when I simplify this out, the limit will now be as h approaches 0 of, ready, 2t over t times t plus h. And I'm going to be minusing, ready, 2 times the quantity t plus h, and this is all over that mess, t times t plus h, and then this whole freaking thing is still over h. Oh, that's nasty. I'm going to keep moving in this direction, and I apologize if you're running out of room on your paper. Okay, so here we go then. The limit as h approaches 0 of, ready, this is 2t minus, I'm going to distribute now, minus a 2t. Yay! I just have an h on top. And on bottom, I have a t times a t plus h. Well, what do you do with that? Well, these cancel out, so I just have an h on top. But I don't, oh, and sorry, the whole thing is over h. Okay, so I still have a nested fraction here. And so I still want to break it apart and do that old school trick that I reminded you of when you learned how to divide a fraction. So this is going to be the limit as h approaches 0 of, ready, h divided by t times t plus h, and that I'm dividing by h. Aha, you remember this rule, remember? So the limit as h approaches 0, you have to flip this and turn it into a multiplication problem. So I have h over t times t plus h. I should have circled this in pink, right? In pink, this is now a multiplication problem, and the h is turned into 1 over h. And ta-da, look, the h's cancel out. That was my goal. That was what I was looking for. Ta-da, I can now say that I have the limit of 1 over, ready, t times t plus h. And if I say that h is going to 0, well, I'm not worried about it anymore because I can throw a 0 in there. It's totally no problem. Ready? And what was the name of my function again? It was f of t. So I'm finding f prime of t, and I'm going to say that that is going to be 1 over t times t plus 0. And hey, t plus 0 is just t, and so my answer is 1 over t squared. Ta-da! Now down here we have one last problem. It says that we're doing the alternate form of the limit definition of the derivative, and it says, hey, can you use this alternate form to find f prime of 3? And it's funny, I taught you how to find a derivative at a point, but I just used the slope formula and a plus h. So what I'm doing is actually like a tricky version of this that isn't even like well represented in the book. So this particular equation might confuse you because I use that other one that we did in class so often. So I am trying to use this, and here is me, trying to set it up. Okay, so right here, if I want to do this at 3, then I will say that I have input and I have output. And my input is that I have x, and the function that he wants me to do is x cubed. And then if I plug in a 3, I'm going to get, ready, a 3 cubed. Okay? You're like, what happened to h? Yeah, this version doesn't have an h in it. So that's why I think it's one of the most difficult versions of the definition of a derivative. So let's just try and see if we can't get through it. Ready, set, go. This is my first, hold on a second. This is my first y value. This is my second y value. So I am going to want to put them in my own order, but take a look at the function. Ready? If I'm just plugging in what f of x is, it turns out I'm not using that order, right? I'm going to use this order right here. That's literally what the function tells me to do. It says just put down what f of x is. Oh, okay. F of x is, ready, is just x cubed. And then it says plug in what happens when you plug in the number that you care about, which in this case is 3. Well, what happens is that 3 becomes cubed. All right. And now what do I do on bottom? What I do on bottom is I do this, x minus 3. And this is, oops, again, the limit as h approaches 0. Okay, so now that I've done that, I'm recognizing the top. That's a difference of cubes, where a is x and 3 is b. And hopefully you remember my SOAP formula, or you have another method of factoring this, because I'm going to factor it right now. I'm going to say that this is the limit as, oops, my bad, x approaches c. This is supposed to be x approaching 3. And it does matter on a test if you write that wrong. So please take my lesson here, that you look at your formula and write down what it has in it as x approaches 3. Okay, so on top I have x, I have a 3, I have an x squared, I have a 3x, and I have 9. And I'm using SOAP. Same would be minus sign, opposite would be plus sign, and always positive is always positive. And now in the denominator, I still have an x minus 3, and how happy I am that those things cancel out, because the rest of this is really quite simple to get to, where I just plug in the 3. 3 is squared. I have a 3 times a 3, which just happens to be 3 squared. And then I have a 9, which just also, I know this is weird, happens to be a 3 squared. That's totally coincidence, by the way. You get a 9 plus a 9 plus a 9, which is a 27. And I a little bit wish that he had come up with a different example for you, like say at 4. And I actually leave it to you. I think it appears in the homework. So good luck. Okay. Good luck.